Now we are finally ready to solve an ODE using variation of parameters. And in fact, let's solve y double prime plus y equals secant of t. By the way, how do you know to use variation of parameters? Well, secant is not one of the functions that undetermined coefficients deals with. It's not exponential, it's not a polynomial, and it's not cosine or sine. That's why we need this new method to solve this. Now, in order to do this, first of all, small detail, you need to put it in standard form. Just like for, I think, integrating factors. So make sure the coefficient of y double prime is 1, which in this case it is. But if we had a 2, you would divide by 2 to make that coefficient 1. And then the second step is look at the homogeneous solution. So look at y double prime plus y equals 0. Again, you do the auxiliary equation, and you find the homogeneous solution is a cosine of t plus b sine of t. Now, what's the idea behind variation of parameters? So here's the main idea. For undetermined coefficients, we guessed our solution to be the same form of the right-hand side. Here, we do not do this. Instead, the idea behind variation of parameters is guess your solution to be the same form as a homogeneous solution. Think of y0 as a building block, and we say, okay, maybe the particular solution looks sort of the same way. So guess yp to be of the same form. Same form. So in other words, assume yp to be not a cosine t, but some function u of t times cosine t plus v of t times sine t. This is called variation of parameters because we are varying the parameters a and b. And this is for some unknown functions u of t and v of t. Why would that work? Okay, why is there any reason to believe that this method works? It's because u and v are very general. They can literally be any functions that you want. So in particular, we will choose u and v to be functions that solve our equation. So that's why the trick here is really the generality of u and v. Now, I will derive this in another video, but if you plug in this ansatz, so if you plug this, perfect. If you plug this thing into the ODE, y double prime plus y equals secant t, and you do one little simplification, you eventually get the following equation. Get that u and v solve the following system. I believe cosine of t u prime of t plus sine of t v prime of t equals 0. So that part will always be 0. And minus sine of t u prime of t plus cosine of t v prime of t, so precisely the derivatives, equals to your inhomogeneous term, which was secant of t. So remember, the beginning we had secant of t, and now we have secant of t. I see, can't you? Okay, now this will be derived in another video, so now just take it by faith and see what we can do with this. Now you may wonder, what in the world does that have to do with Cramer's rule and the Wronskian? Well, notice you can actually rewrite this in matrix form, and what you get is the famous var of par equations, namely the following. The coefficients are just cosine and sine, and then minus sine and cosine, and then u prime v prime, and then always 0 and always the inhomogeneous term. And notice this left-hand side is precisely, the Wronskian matrix. The Wronskian matrix of what are homogeneous solutions, cosine and sine. So really, the mnemonic, if you want, what is the form of this equation? Wronskian matrix u prime v prime, because we also always want to integrate, and then 0 and inhomogeneous term. That's an easy way to remember this. And the next question is, how do we solve for u prime and v prime? That's where we use Cramer's rule. Okay, so let's do that now. So step 4, I believe. Solve using Cramer's. So I want to remind you what our equations are. So it was cosine t sine of t minus sine of t cosine t. So the Wronskian of cosine sine u prime t v prime t equals 0 secant t. Now, what is u prime? So if we apply Cramer's rule, so u prime t, the denominator is our original matrix. So cosine t minus sine t, sine t, cosine t. And the numerator, remember, you take the same matrix, but replace the first column by your right-hand side. So 0, secant t, and then sine and cosine. Sine of t and cosine t. And then you do it, and you'll see it's not that bad because there is a 0 term. So 0 cosine t minus sine of t secant t. And then for the denominator is cosine t, and then minus sine t times minus sine t. It's minus sine t. And if you look at the denominator more carefully, that is in fact cosine squared plus sine squared, which is 1. So we get minus sine of t secant t over 1. But remember, secant is 1 over cosine. So you get minus sine of t over cosine t, and really minus tangent t. That's one thing. U prime simplifies. Now, for V prime, same thing, but you replace the second column by the inhomogeneous term. So in this case, V prime of t. So I believe we had cosine and sine. Cosine t, sine of t, and then 0 secant t. Now, for the denominator, the good news is you don't need to repeat this because it's still the same matrix as before, whose determinant was 1. So let's clean this up a little bit. Minus tangent of t. So we're just left with cosine t secant t minus 0 times sine t. Now that's cosine times secant. So cosine t times 1 over cosine t. And that's 1. Now we get u prime and v prime. But what we need to do, we need to find u and v. So the next part is to integrate. I know, lots of steps, but they will always be the same thing. So integrate. So u prime of t was minus tangent of t. So u of t is integral of minus tangent of t dt. And remember, integral of tangent is ln of secant. So in this case, minus ln of absolute value of secant of t. And that gives you u of t. And you may wonder, what about that constant? Why not plus c? That's because, remember, we just want to find one particular solution. So 1 is enough. But if you added the c, you will see it's interesting. It just gives you the homogeneous solution. That was the hard part. Then v prime, I believe, was 1. So c'est la v of t is integral of 1 dt. So v of t equals t. And then we get our homogeneous solution, sorry, our particular solution. So remember, yp of t was u of t cosine of t plus v of t sine of t. And then we finally get our particular solution is minus ln of secant of t times cosine of t plus t sine of t. And last but not least, what is our final answer? Step 6. Answer y, our solution is the homogeneous plus the particular, and so y of t is a cosine of t plus b sine of t, and then all this. So minus ln of secant of t cosine of t plus t sine of t. Who would have guessed that? I mean, good luck doing that with undetermined coefficients. It wouldn't have been possible. But I do want to say again, what's nice about variation of parameters is it works every time. It works every time. And also, as I said, there is no guessing involved. In particular, note, for var of par, there is no need to check for resonance. Check for resonance. There's literally no exceptions for var of par. You just do it. Very good. And in the next video, I will show you how to derive those equations. And then I'll just do one more practice example.